Hey, I am here to talk to you for a couple of minutes about moles some more. As you know, we have already talked about the mole and how we deal with it in chemistry. Remember that it represents a huge number that's impossible to count, right? Because it's representing something very tiny. And because of that, we have to have a different way to measure moles since we can't count them. What we're going to be talking about next is how we handle gases. And I want you to think about gases for a minute. Remember, gases are very small, right? They're very small, but they occupy a lot of space. Very small, but they occupy a lot of space. In other words, they, have kind of bigger volumes. So when we think about a gas, if we want to measure a gas to find out exactly like how many atoms are present or molecules are present, how many moles there are, it's sometimes very difficult to take a sample of a gas and put it on a balance. Maybe because our sample is really, really small. It has a very low mass. It'd be tough for it to register. Maybe also the gas is hard to measure because it, is in some kind of like a balloon or something so that it can't just stay on the balance. So what we have is another conversion fact that we're going to use when we're talking about moles and gases. And this is actually how they originally came up with the idea of the mole. Remember in our TED Talk, we saw that Avogadro decided this fact or discovered this fact about moles and gases long before it was ever accepted, like how many atoms and stuff were represented. So it's kind of interesting thing. Okay. So there's actually two different ways that we handle gases. Today, we're going to specifically talk about gases when they are at something called STP. All right. So here's what we need to know. At STP, 1 mole, and this is true for any gas, is going to occupy a volume, or it's going to take up space that's equivalent to 22.4 liters. Now, a few things I want to point out about here. Notice that it's for any gas. It doesn't matter which type of a gas it is. So whether it's hydrogen gas or water vapor, or carbon dioxide, or any other gas that you can come up with, if it's held at STP, then the volume that that gas will occupy is 22.4 liters. So 1 mole is equal to 22.4 liters. Now, some of you have probably never heard of STP before, and that's fine. What this refers to is something called standard temperature and pressure. And it's really not like normal conditions that you find out and about. Like right now, our classroom is not at STP. These are conditions that you would establish in a lab, and standard temperature says that the temperature is 0 degrees Kelvin, or I'm sorry, 0 degrees Celsius. And we'll talk more about temperature next week when we talk about another way to measure gases. And also it's measured at a temp or at a pressure of 1 atmosphere. And you're probably not terribly familiar with that unit yet, and that's okay. Also, it's just another common unit that we use. You've probably heard of like millimeters of mercury because that's what they use to talk about the weather, and that's fine. But this is more of a standard accepted unit that we use when we're measuring gases. So STP means that we are at 0 degrees Celsius and 1 atmosphere of pressure, which is really something that you'd have in a lab. And again, it means that 1 mole of any gas will have a volume of 22.4 liters. So this is what we really need to know here. Okay. Now, we have just spent so much time practicing doing calculations involving moles and grams and using conversion facts that looked very similar to this. Nothing else is changing here. The process of solving these problems is the same as it was for the grams, for going moles to grams. Now we're just using a different conversion fact. So we're going to do 4 examples together here really quick, and then you'll get to go and work on your own on, I have 6 practice problems for you to complete. So example number 1, it says that we have a container with a volume of 893 liters, and we want to know how many moles of air that is at STP. Okay, so it clarifies that it's at STP. So here's the conversion fact that we're going to use. Remember that our given is always the number that's in the problem. So the number that's in the problem is 893 liters. Now, in order to convert liters to moles, we have to use our conversion fact that 1 mole is equal to 22.4 liters. That's the conversion fact we're going to use. Notice that there's no mention of mass or grams here, so we're not dealing with those in this problem. It's just going to be this particular conversion fact. And like we have done all along, we're going to take our given and we're going to multiply it by a fraction, right? And the fraction, the numbers from the fraction are going to come from the conversion fact. And we put the numbers on either the top or the bottom based on what we need to cancel. So since there's liters on the top, we're going to put the 22.4 liters on the bottom. And again, we do that so that the word liters cancels and we put 1 mole on top. And of course, all we have to do to solve the problem is the math. And anytime we multiply by a fraction, we're going to multiply the top and we're going to divide by the bottom. So for this particular problem, we're going to get our calculator and we're going to do, let's see if you can see that. Oh, you sure can. Okay, you're going to do 893 times 1 divided by 22.4. And our answer is 39.867 or 866. We'll round to 2 decimal places. So I said 39.87 moles. It's a lot of moles, right? A lot of atoms. We definitely wouldn't want to have to calculate or count all of those. Okay? All right, let's look at another example one. A chemical reaction produces 0.37 moles of nitrogen gas. What is the volume that that gas will occupy at STP? And again, the fact that it's at STP is very important. Next week, I'll talk to you about gases that aren't at STP. Okay, and we know that at STP, 1 mole of any gas occupies a volume of 22.4 liters. So if we have 0.37 moles of nitrogen gas, we want to know what volume will that amount take up? Like how much space will that amount take up? So again, we're going to start with our given from the problem, 0.37 moles. We're going to multiply by the conversion fact, right? And we're going to write the conversion fact into a fraction based on what, what will cancel the unit. So if I have moles on top from my conversion fact, I want to pull moles onto the bottom so that the words can cancel. So I put 1 mole on the bottom and 22.4 liters on the top. And again, the way we solve this is we multiply across the top of the fraction, we divide by the bottom. So 0.37 times 22.4 divided by 1, and we get 8.288. And we'll just round that to 2 decimal places, so we get 8.29 liters. And that's the volume of my sample if I have that many moles. Okay, pretty straightforward. Notice that the conversion fact is always the same. Unlike mass problems, the mass changes based on the identity of the element. Here, it doesn't matter. We worked with air in number 1. We worked with nitrogen in number 2. So that conversion fact, 1 mole is equal to 22.4 liters, is very important. All right, let's look at the next problem. It says, in an experiment, 12.1 grams of dry ice were converted to gaseous carbon dioxide at STP. What was the volume of that gaseous carbon dioxide? So in case you don't know, CO2 goes straight from a solid to a gas, right? It's called sublimation. And so in this problem, we're starting with 12.1 grams. Now, here's the problem. If we look back up at our original conversion fact, there's no mention of grams here in the problem. So in order to find out the volume, right, because that's what we're looking for is volume, that's liters, we're going to need to first take these grams and convert it to moles using the molar mass. And then once we know how many moles we have, then we can convert that to liters. So this is a 2-step problem, all right? So step 1, we're going to calculate the moles. So we're going to start with 12.1 grams. And again, we're doing carbon dioxide, so that's CO2, right? What do we have to know about CO2 in order to convert grams to moles? Well, we have to know its molar mass. What's the mass of 1 mole? So you would need to go through and do the work. And so you do 1 carbon, which is 12.01, plus we need 2 16 grammars for the 2 oxygens, which is 32. So we add those together and we get 44.01 grams. So 1 mole of CO2 has a mass of 44.01 grams. We're going to take that conversion fact and write it as a fraction here so that we can get rid of grams and have moles. Okay, so I'm going to put grams on the bottom so that grams cancels from my given. So 44.01 grams on the bottom, 1 mole on the top. Now I'll go through and do the math. Again, I multiply by the top and I divide by the bottom. So 12.1 times 1 divided by 44.01. And the answer is 0.27 moles of CO2. But keep in mind, we aren't quite done because the next part of the question is what was the volume of that gas? And again, remember that it was held at STP. In other words, how many liters of CO2 do I have if I have 0.27 moles of CO2? So we have to do a second calculation. This time we're going to use the fact that 1 mole of any gas is equal to 22.4 liters. So I'm going to take my 0.27 moles and I'm going to multiply it by that new conversion fact so that I can get rid of moles and have liters. So I'm going to take my 1 mole and put it on the bottom and the 22.4 liters on the top, right? Remember how I mentioned when we first started doing this that the process is the same over and over again. The only thing that changes is the mass. Here's another great demonstration of that. The process of unit analysis is always the same. Once you master the idea that if you have a number on the top and you want to get rid of it, then you need to put it on the bottom of the fraction. These should be very easy. So now we just have to do the math. Again, we're going to take our given and we're going to multiply it by the number on top and divide it by the number on bottom. So in this case, we're going to do 0.27 times 22.4 divided by 1, and we get 6.05 liters. And that is the answer to our question. Okay? All right, last problem that you may encounter, and this one is very similar to problem number 3. Okay, it says that a chemical reaction between acetic acid and calcium carbonate produces 18.6 liters of CO2 at STP. How many grams of this gas will be produced? Again, remember that we don't have a conversion fact for going straight from volume to grams, but we do know that we can take our volume and convert it to moles. And then once we know moles, we can use the molar mass to find the mass at the end. Okay, so as always, we're going to start with our 18.6 liters, our number in the problem. And in order to find grams of this, I have to start by finding the moles. Okay, so I'm going to calculate the moles here. To do that, I'm going to use the conversion fact that 1 mole is equal to 22.4 liters. And so I have to pick what needs to go on which part of the fraction. So I'm going to put the 22.4 liters on the bottom and the 1 mole on the top. So I'll do 18.6 times 1 divided by 22.4. 18.6 times 1 divided by 22.4. And I get 0.83. We're just going to round to 2 decimals. So I'm going to put this over here. 0.83 moles of CO2. So I know exactly how many particles of CO2 I'm dealing with in this problem. But again, remember the question asked for the mass, how many grams of this will be converted. So the second step is to take our moles and convert it to whatever we're looking for. In order to do this, what do I have to know about CO2? Good, I need to know the mass of 1 mole of carbon dioxide. So again, we're going to figure that out. We're going to add carbon and 2 oxygens together. I think we did that in the previous problem, right? So we can just pull that number down from over here. We know that 1 mole of carbon dioxide is equal to 44.01 grams. So 1 mole is equal to 44.01 grams. And then we're going to take our 0.8 moles, 0.83, I apologize, moles of CO2, and we're going to multiply it by a fraction using our conversion fact. Now, if I have moles on top, then I want 1 mole on the bottom to cancel the units, and then I can put the 44.01 grams on top. Then again, all I have to do is the math. I'm going to multiply across the top of the fraction, and I'm going to divide by the bottom. So 0.8 times 44.01 divided by 1 is equal to 35.21 liters. Oh, actually, just kidding, grams. We're looking for grams here. Okay. So there are 4 example problems that are very similar to what you're going to see in your practice problems. What I'd like you to do next is take what I just taught you. Remember, what I just taught you is that 1 mole of any gas will occupy 22.4 liters. So yes, their masses can vary because, again, we can be dealing with very small gases like made up of just hydrogen, or we could be dealing with huge gases like iodine turns into a gas. Regardless of the size of the particle, we know that 1 mole of any gas is going to occupy 22.4 liters. So if we keep this in mind and we get this down in our thoughts, then when we read a problem, we just have to keep track of what we're doing, right? If we're starting with grams or liters or mole and where we're converting to. So like I mentioned before, you're going to head to Google Classroom and check out, there is a homework assignment. It's the mole calculations number 3, and it is due by Sunday. If you get that taken care of, that'll allow me to look it over and get us prepared for class the following week. All right, have a great day, and we'll talk to you later.